Good morning and welcome to this second part of this presentation on the case studies of Cingoli Municipality, Town Hall and the Bell Tower. It's a case study that is able to illustrate the issues that you may encounter with historical buildings when historical buildings are used as town halls, museums, schools, sometimes also hospitals, so that there are some compromise between the safety level, the use and the protection of the building. During the first part of the presentation we have seen all the knowledge phase, meaning all the available documentation on the palace and on the bell tower, starting from the history of the construction, going through all the recent intervention that the palace and the bell tower undergone, and arriving to the survey campaign that I have implemented in order to complement the existing data. In the second part of the presentation we will see the assessment in terms of both models and numerical analysis and results in the actual state, and then integrating the actual state with some intervention which are compatible with the historical value of the building, and we will draft some conclusion at the end. So for this part, I would like to start with the general parameters of the analysis. Then we will go through ground motion, so the design earthquake, and then we will go to the different model and analysis that have been considered, the comparison of the results of the analysis with the damage suffered by the 2016 Central Italy earthquake, and then we will go to the response of the building to the design earthquake and identified vulnerability. This is for the assessment in the actual state. So, general parameter. First of all, the analysis has been done for the only seismic loads. Vertical loads has been disregarded. This is a seismic safety assessment, so it's not a comprehensive assessment of the building. According to the Italian code, it is possible, or it was possible, because this analysis was done with the previous code, not the actual one. It was possible to evaluate the ultimate limit state only, so the life safety conditions, and not the damage limit state condition. Nowadays it could be possible also to evaluate the damage limit state condition, but with some limits that should be somehow agreed between the client and the engineer, so there is no strict prescription on this, while the ultimate limit state is the classical, let's say, limit state that is analyzed in existing building. The nominal life of the building, as for ordinary building, is 50 years. But then the use of the building, the importance class of this building, which has been assumed in the analysis, is important class 4 for the town hall use of this building, increase the nominal life twice in order to have the reference life. So reference life is 100 years, and if you assume for the ultimate limit state 10% of exceedance, we have a return period of the earthquake of about 1000 years, 972. All the analysis will be performed in terms of risk index. This will be the output of every analysis, and this risk index is defined as capacity over demand. It could be flexural capacity over flexural demand, it could be shear capacity over shear demand, and so on. So it means that if this value is greater than 1, the building is fully retrofitted or fully compliant with the code as for new buildings. While if this risk index is 0.5, it means that the capacity of the buildings is only 50% of what the code foreseen for a new building. Let's move now to the ground motion at bedrock and surface. The seismic history of Cingoli municipality shows several earthquakes in the range of 7.5 Mercalli-Cancani-Seeberg intensity. Consider that the Mercalli, modified Mercalli intensity, it's 1 degree more or less than this Mercalli-Cancani-Seeberg scale. So earthquakes were not very strong in the past. However, you can see from the catalog that the catalog is for sure incomplete, because we have data only from 1700. So in order to understand the let's say the hazard, we have really to go to hazard analysis, and the hazard map of Italy, it's shown to the right, and Cingoli is located here in this yellow area, which is moderate seismicity, as we already said in the previous lecture. Going to really numerical values, for 475 years, so for ordinary building, the peak ground acceleration, the design peak ground acceleration, it's 0.17 g, while if you go to important class 3 and 4, this value increased to 0.2 and 0.22 g. So basically this is the value that we have to consider for flat soil, rigid and flat soil, so on bedrock. But then there are soil effects and also topographic effects, so stratigraphic and topographic. According to the stratigraphy, it could be considered like a soil type B, with 1.2 increase in peak ground acceleration, and due to the topography, we are seeing that we are on a crest, and this gives another 20% of amplification. So this means that the total amplification is in the order of 1.4, and the peak ground acceleration, the design peak ground acceleration for 950 years return period, is 0.32. 0.32, it's quite considerable. So even if we start from moderate seismicity for ordinary building, 0.17 on flat soil, then considering the soil and considering the important factor, we get a value which is quite important. Also, site response has been performed. Even if you are in a crest, so not in a real ideal stratigraphy for considering 1D model, local site response with 1D model has been performed with 3 layers and several accelerograms, and the results is that there is some peak in the response for short periods, according to the fact that the contrast of impedance, it's in the order of 12-13 meters, so it's not so deep. And according to this stratigraphy, obviously the resonance of the soil is in the short period, so the amplification in the spectrum is in the short period. Some 2D analysis has been performed in the microzonation of Cingoli municipality, so some results has also been considered and compared in terms of 2D and 1D soil amplification, and the results again is that in the short period there are some amplification on the crest. You can see on top of this crest there are the highest amplification, while there are the amplification at the end of at the border of this crest. This is quite known and well known, and so the analysis confirms a little bit what was expected. So at the end we have in terms of spectral acceleration, we have the green spectrum, which is the Italian code for soil B on crest. Then we have local site response for the analysis we have performed, or for available data in case of 2D, and it appears that for short period the amplification is greater than what is foreseen in the code, while for higher period these side effects are lower. Again, this is I told you it's in good agreement with the soil stratigraphy. I also wanted to compare this design spectrum with the 2016 Central Italy earthquake. So we have seen that the magnitude of Central Italy earthquake is 6.5, and the distance of Cingoli municipality from epicenter is in the order of 60 kilometers. So from this, and considering some attenuation relationships in terms of spectral ordinates, several spectrum has been obtaining, and averaging all of them, one can get the average expected spectrum of that earthquake at Cingoli. And then it has been considered the amplification due to the side response, so including also this effect in the expected spectrum. The results, it's the blue line. It's the blue line. So you can see that it is in the order of 0.25, 0.30, while the maximum spectral acceleration in case of soil effects is 1.2. So we are in the order of at least I would say 4 times more the design earthquake. So this is important to understand also the relevance of the cracks with respect to the strength of the seismic action, to the power of the earthquake, because some cracks were there, and if the earthquake is very low, this means that there is high vulnerability, while for small cracks, if the earthquake is the design earthquake, then it can be acceptable. Models and analysis. Several models has been considered according to the different behavior of the palace and bell tower, and in more detail. The first really simplified model, which is mainly used for new buildings, and it is based only on cross-sectional area. This really gives only an idea of the percentage of the resistant wall in both directions at the different floors. The second model is a non-linear static analysis model through macro element. And this has been introduced to analyze the palace and the tower in case they can be supposed perfectly connected each other. We've seen that the connection, there is some connection, but it's not continuous all over the height of the bell tower. So since this connection is somehow uncertain, it is useful to analyze 2 different models, one for the palace and bell tower connected, and once for the bell tower and palace not connected. In this case, when they are not connected, the bell tower will not exert forces on the palace. So for the palace, it is enough to consider the model when they are connected, while for the tower, it's proper to consider both models and check which is the worst one. For the non-connected tower, so in this case, a linear dynamic analysis continuous beam model has been introduced because of its simplicity. It's possible to analyze it in closed form with some spreadsheet which give you immediate results and feelings, I would say, of what happens. For the out-of-plane failure modes, some different possible models have been implemented, linear and non-linear, and they are independent from the in-plane models. All the 3 models that I shown you before, I told you before, are in-plane models. So the behavior of each wall is just considered on its plane. For the out-of-plane, they are independent model. So for this simplified model of cross-sectional areas, just important to notice that according to the minimum area, sectional area of the code, based on the number of floors above the floor considered, In our situation, in the x direction, this floor sectional area or floor sectional percentage in terms of resisting area of the walls over the total area of the building, it's far more than the minimum. While in the y direction, there are some floors where this percentage is very similar to the minimum. Considering that this table is valid for, this minimum are valid for new buildings where the resistance of the masonry it's greater for sure than in the case of existing building, especially if the quality of the masonry is not so high. One would argue that at least in one direction, in the y direction, there would be some for sure some issues. Tower, isolated tower, as I told you, continuous beam model. In any case, discretized for simplicity of the analysis. And only 3 modes have been considered because with this most of the mass of the tower has been considered, and at the different height of the buildings, the modes and the participation factors and then the modal forces are considered, and then the resultant in terms of axial forces, shear and moment, quite standard dynamic analysis. For the palace and tower connected, in this case we have to go through finite element models, and in this case the Tremuri software has been used, considering several floors and including in the model of the opening of the window doors and the different floors, also different height. It has been a little bit, not too much complex, but in any case not simple to include all these elements in the model. Or at least there were several options, and there were investigated also several options for modeling the different opening and floors. Tremuri software, I'm aware that you know that software, so will not spend too much time. Just to remind that it's the macro element of this model has some let's say flexural behavior at the end and shear behavior at the center. So in this point the failures are analyzed, and then an overall let's say non-linear behavior it's considered in analysis, which includes shear failures and flexural failures according to the different modes. And it's very user-friendly in terms of visualization of the results, because each element has different colors according to the type of failure, if it's flexural, if it's shear, and according to the damage state. So if it is undamaged, or if it is plastic or collapse. So this gives you immediately an idea of where you may encounter problems in your buildings and which type of failure do you expect. The model is an in-plane model for any, let's say, for the walls, and where the walls intersect, then there is some sort of interaction between the perpendicular walls, and this way a 3D behavior can be simulated. The analysis it's a non-linear static analysis, so several pushover curves can be obtained according to the direction of the forces applied and according to the different shape of these forces along the height of the building, if it's linear, if it's triangular, no, if it's constant, and so on. For the out-of-plane overturning, several walls have been considered, in particular in the large council hall, where the theater was, where the height and the length are significant. So in this case, probably let's say the out of plane behavior can be activated without interacting the two perpendicular walls, because at a certain distance there is no any more effect of the constraint of one wall on the other wall. So several models have been introduced for this out of plane analysis. The static analysis that gives you the onset of the overturning, the linear kinematic analysis that give you also some sort of behavior during the overturning, but with some linear hypothesis, and then the more complete non-linear kinematic analysis that includes also large displacement on the analysis. And this has been done through again some ad hoc realized Excel spreadsheet, because again it's more simple to visualize all the parameters, and it's simple also to introduce different options. There are also software available for this. Even Tremuri has some additional software, additional part of the software that is able to analyze this. But if you want, for example, to analyze the effects for the code spectrum, then for the spectrum of the 2016 earthquake, then for the side effect spectrum, the spectrum that includes local site response. So if you want to change all these parameters very easily, then it's probably better to have an Excel spreadsheet rather than going into a more general let's say tool like Tremuri that maybe make some assumption that you are not able to control or to change. So what is the response to the 2016 Central Italy earthquake? To the left of this picture you can see the results of the analysis just for the bell tower, and to the right, in the right part, the results of the analysis for the model where the bell tower and the palace are connected. So in this graph, along the height of the bell tower, we can see the ratio capacity demand, so it's the risk index, and you can see that in the bell tower it's always greater than 1. Only in the belfry, because of this opening and this the behavior that appears due to the openings. So one part is compressed, the other one is under tension, and the part under tension reduce the strength. So there is a significant decrease in capacity just in this part. For all the remaining part is well greater than 1. So we expect some damages also only in the belfry from this model. And for the global behavior of the building, you can see that most of the building is green, and in the belfry there some damage are expected but not collapse. It's not a dark red, it's light red, so it's plastic, but it's not collapse. And few damages are also in other elements of the palace, but very small in number and in extension as well. In terms of capacity demand, a risk index for the global behavior, it ranged from 0.7 more or less to 0.9 according to the different directions. And this again proves that globally it's we expect some damage, but not so severe. And this is exactly what happened in reality. If you remember, there were cracks on the belfry, and there were some short-term countermeasures also implemented to stabilize these cracks. Here it is, but very small cracks on the other part of the palace and tower. So I would say that the model reproduced quite consistently the observation during the 2016 earthquake, and due to this, we can analyze the design earthquake in a quite reliable way, because the model is validated through observations. So, which is the response to the design earthquake at this point? If we consider the tower alone, and again we can see that in general the risk index, so this capacity over demand ratio, is less than 1. Along the bell tower it's almost 0.5, and goes practically to 0 for the flexural behavior in where the openings are. Again, in this part there is compression and tension, and this means that when it is in tension, completely in tension, then the resistance to flexural is 0. So this is the reason why flexural behavior goes to 0. Why shear behavior, at least in the compressive part, there is still some capacity to resist shear. In the tension part, no. And so this is again why it reduced to almost 0.5. Again, one can note that the response is bigger for the second and the third mode. It's larger because the spectral acceleration for the second and third mode is much bigger than the spectral acceleration for the first mode, and this is obviously due to the fact the first mode has 1 second period of vibration, while the second mode and third mode are much stiffer, and so the response goes in that part of the spectrum with higher responses. So this is typical of tall buildings, of chimney, bell towers. Second, third mode are more significant than the first mode. So for the shaft, we can summarize the risk index is the order of 0.5 when the tower is isolated, and for the belfry is in the order of 0.17. For the global behavior, several pushover curves were performed on the building. I analyzed the case of full stiffness and reduced stiffness to 50%. This is allowed by the code in order to consider the presence of cracks during the response of the building. The risk index changed a little bit, but not so significantly, from 0.11 to 0.13 in case of reduced stiffness. The period of vibration of the building is in the order of 0.93 is the maximum period with reduced stiffness when the elements are considered cracked, while it is in the order of 0.7 seconds when they are not considered cracked. So this is the pattern of the damage in the palace and bell tower along the two directions, the X and the Y direction, and we can see basically that all the damage concentrates on the belfry with some collapses. So the belfry is expected to collapse, and this somehow stops not stop the analysis, but it's the first element that collapses, and then it's not possible to increase the damage in all the other elements because this is already collapsed, and so there is no increase in capacity in the building if we control the top of the bell tower, the movement, the horizontal movement or displacement of the top of the bell tower. In the Y direction, still there are some expected damages in the belfry without collapse, and some shear or flexural damage without collapse in all the building. But again, this is because the belfry collapses. For the out of plane behavior, according to the different walls, the transversal and the longitudinal, and according to the three models, quite different results in terms of risk index can be obtained. In particular, for the linear analysis, it seems that the longitudinal wall has a lower risk than or a greater risk, sorry, a lower capacity than the transversal wall. while for linear kinematic analysis they're quite similar. And if we go to the nonlinear kinematic analysis, so we consider the larger displacement, the nonlinear displacement during the out of plane, then this capacity increase quite significantly. So one has to make some judgment about the different worlds and about the different models. So what are the identified vulnerabilities in the buildings after both the knowledge phase, because maybe not everything can be included in the model, and the results from the model. So for sure, one of the main issues is the fact that the mortar is degraded, especially when the bed joints are not repointed, and this gives very low resistance to some type of walls. There is lack of effective connection between orthogonal walls. This has been considered in the analysis for the bell tower and the palace. They have been considered connected and not connected with two different models, but probably even other walls are not connected. It's almost impossible to evaluate all the connection if there are not, and having so many models. Sometimes also the non-connected models are considered, but maybe this is too much conservative in this case, because in some cases we have observed a good connection. The council hall walls are not restrained on top, or they are connected. They are connected through the truss, but this does not impede the out of plane overturning of both walls at the same time in one direction, because the movement of the top part will be the same, so there will be no effect of the ties on top, but so some sort of restraint should be included on that part. The belfry tower has for sure some insufficient capacity, and also the shaft of the bell tower, we've seen that has a lower capacity. There are other elements in the palace and in the porch columns that may suffer from some damage, and elements that have not been considered in the models but has to be somehow considered in the possible intervention is that one wall at ground floor, it rests on vaults and not on another wall. It's not a huge wall, but in any case it has to be considered, and the council hall partitions are not anchored to the top. So these are the main vulnerability of the building. Again, I want to stress that in this one has to consider both results of the model and expert judgment from all the elements that has been somehow known and analyzed during the knowledge phase, because not everything is possible to introduce in the model, so one has to make this sort of merge of information, of different sources of information. Let's pass now to the incremental intervention analysis. What does it mean? That it's possible to analyze the buildings according to the different incremental intervention. The first intervention try to solve the most vulnerable situation, and then the other intervention solve all the other situation. This means that according to this procedure, the risk index should in terms of capacity demand should increase as long as additional intervention are analyzed. If you analyze just different intervention, you may have results where the risk index can be higher or lower according to the type of intervention. If you decide to use reinforced concrete jacketing, or for example injection or base isolation, I don't know, maybe you can get very different results, and without any let's say connections between the intervention. With this incremental interventional analysis, one is expected to always increase the safety level, because you're addressing the vulnerability of the element that is in that moment conditioning all the global behavior or the local behavior, and so the risk index. So according to this, according to what we have seen, the first intervention is on the belfry tower, because it's the first that collapsed. Then the tower shaft. Then we go to the palace, injections on the palace walls to improve the mortar quality. And then if we want to increase, we have to have some fiber reinforcing materials on one or both sides of the palace wall, and then also some out of plane countermeasure. So we will see what happens when we introduce this sequence of intervention. So for the belfry, obviously there are different possible interventions. In this case, I analyze inserting a steel frame around the openings in order to stiff the openings and to provide additional resistance. And in the model, they are inserted through this element that you may see in this part. It is equivalent to 3 steel profile 300 millimeters depth. The global behavior has been analyzed again, and the risk index turned out to be 0.3. So there was really a significant increase in capacity of the building, of the palace and the tower. From these pictures, from these patterns of damage, we can see that the element that at this point is damaged is the tower shaft, from the top of the palace to the belfry. So it means that the second intervention has to address this vulnerability, so has to increase the resistance of the tower shaft. To this end, 2 different interventions has been considered together at the same time. Is the injections of the wall, because in the analysis I suppose that the inside part of this wall, they were 1.4 meter thick, the inside part has degraded mortar, so only the outer joint were repointed. That's my assumption. That has to be validated obviously once the intervention will be designed and implemented in reality. So if it is really needed inside, there should be some injections, and at that point the masonry is able to sustain additional vertical loads, and with this vertical press stressing it is possible to increase vertical stress and consequently the shear resistance and the bending resistance, because you know that as long as the vertical forces increase, unless they are too much obviously, there is an increase of shear strength because of attritive behavior, and there is an increase of also the flexural strength. So once this intervention is implemented, and I also consider to have on top some shape memory device, shape memory alloys device, in order to keep this vertical force constant. So in the analysis, just vertical forces were added, and at this point in the analysis for the different pushover curves, I obtain this pattern. Basically, it's not anymore the shaft, the element that collapsed, but this but there are some elements in the palace. This is the block stairs on the back, the top level, and this is one wall at the second story. So at the level of the council hall where the theater was. The increase in risk index It's not very much with respect to the previous situation, because it is almost the same, but the failure mode changes. So it's not anymore the bell tower, the shaft of the tower, it changes to another element. So also these elements now has to be retrofitted. So the next step is injections on palace walls in order to increase their resistance. While the first step is injection, because if we use jacketing on both sides, could be, now we don't use anymore reinforced concrete jacketing, we use fiber reinforced cementitious material jacketing or other types. If you use this type of intervention, the inner core of the wall will be always with poor resistance. So we will strengthen the sides, but inside it will remain the same. And with so large thickness, it makes a little bit nonsense to strengthening the exterior part with 5 centimeters of addition of this material, while 1.5 meters in the center remain with the same degraded mortar. So the first step is being considered the injections as necessary step for further intervention on the walls. So it's also worth to analyze what happens only in the case of injections, because maybe you can stop there. And to do this, I have performed a preliminary experimental test to check if the walls can be injected, and which is the percentage of mortar that can go into the wall. Because you know that there are some type of masonry where a lot of materials can be injected, you don't know exactly where it goes, or there are other masonry where it's not possible to inject because there is no continuity of the voids. So this has to be investigated before proposing any injection intervention, because otherwise at the end you may turn out that you may find that it's not that intervention is not possible to be implemented. So this test has been done in the attic, in just below the roof, because that part was not used, so it was possible to make this test, and the test was done in an area of 1.6 meter times 1.9 meter, and there were 3, 5, 8 holes that were performed in the wall, arranged in a quickshanks, let's say, shape, and with the standard procedures, some mortar was injected in the wall. At the end, we found out that basically there were around 20 liters per cubic meter of masonry, and this is supposed to be about 8% of the mortar volume, which is not a huge number. And this means that probably, at least in this case, the voids were not very much, or were not connected. So probably what I would suggest in this case is to perform also some tests with flat jack before and after the intervention, to check exactly the increase in resistance, and not to take just the standard value from the code that tells you that maybe for this type of masonry you can have an increase of maybe 1.5 or 2 times the resistance for the resistance of the masonry. Because really the increase of resistance depends on how much you inject, how much you at that point you have a new let's say cohesive material inside your wall. So not all the masonry walls can be injected, for sure. The full brick masonry walls cannot be injected. These are on top on the tower or on the facade. So in this part also the square block masonry walls, it's impossible to inject. So all the first floor, the base, the underground story, all these walls has not been considered injected. So again, a very detailed study of which wall had increased resistance and which wall remained with the same resistance, and then another analysis, I mean, in this configuration, additional analysis has been performed. Not only the increase in resistance has been considered in the element, but also an increase in resistance. According to the code, it is an increase of stiffness of 2, and the strength increase again it's 2, because the quality of the mortar of the masonry it's such that the injection has, I mean, a significant increase, while for other types of masonry it's not so significant, the increase. But as I told you, I suppose that only the most vulnerable walls were injected. So in this case, the analysis showed a significant increase in the capacity of the building, and the seismic risk index reached 0.42. The failure modes at this point were in some part of the facade, in some elements of the transversal wall. A little bit jeopardized, so at this point it's not easy, and even probably also not reliable to say, okay, I'm going to retrofit exactly this wall, because it seems a little bit too specific points, which in reality the damage could enlarge to other wall as well. So the next step is not addressing specifically this wall, but in adding to the injections the fiber reinforced intervention on the palace wall. You are very well aware of this type of intervention, and it can be on one side, it can be on two sides, and it can also be the so-called reinforced repointing, which is inserting a this red one, a very flexible steel mesh in the bed joints. So this solution is for the two-side intervention for walls that are plastered on both sides. The one-side intervention is for walls that can be, let's say, that are visible on one side, and so you cannot plaster them. The Ministry of Cultural Heritage will not allow you to do so, and in such case the reinforced repointing can be implemented. So again, a very detailed study of which wall can undergo this type of intervention. But before this, I considered that the thickness of the wall were really significant in this case, from 1.4 to 1.8 to even 2.3 meters. So adding just 5 centimeters laterally, with this fiber mesh, it could be quite different from the standard value provided in the code for this type of intervention, which, as I told you, gives the increase in strength and the increase in stiffness with respect to the original configuration. So hopefully the producer of this type of materials as a tool available on the web, which is able to evaluate the increase in resistance according to several experimental tests based also on the thickness of the wall. So I ran several analyses of this tool, and I plotted the results against the thickness of the wall. In this case, again, the thickness of the wall over the standard 600 millimeter thickness as a reference thickness. So you can see that as the thickness increase in the vertical axis, there is the relative, let's say, increase of resistance, again normalized to the resistance, the increase of resistance for 600 millimeter thickness. So basically, if for 600 millimeter thickness you have a certain increase of resistance, if you go to 3 times more in thickness, so it means 1.8 meter thickness of wall, you have a reduction of 40% of the shear strength, reduction of the increase of strength, and the same changes for the stiffness. So basically, with this preliminary analysis, I was able to evaluate for every thickness which is the increase of strength. And if we compare this with the standard value in the code for the seismic code and this disordered, let's say, masonry, the code provides for the jacketing 2.5 times increase in strength. While if we perform this analysis, if there is on one side only, on one side only the intervention is 1.8 increase. If it is two sides, it is more than 3 times increase. And if it is one side plus on the other side the reinforced repointing, so that mesh without additional let's say cementitious materials, it is 2.1. This for the standard thickness of 600 millimeters. So even in this case, you can see that the value according to the code is just an average value, but if you make the intervention on one side only, it is quite lower than the value provided on the code. So this allows to differentiate wall by wall in terms of the type of intervention which I decided to implement on that wall according to the situation, if it is plastered or not, and also according to the thickness, including these relationships with a regression of the numerical analysis based on the tool that I told you available on the web. So these are the tables with all these final values of resistance and strength of each wall, and what are the results at the end. The increase in capacity and the risk index is there. It reached 0.49, so there is some increase. And the elements that collapse are always more or less the same as before. So we really didn't solve the problem even with increasing the overall resistance of the wall. Still these elements collapse. Okay, so for the out of plane countermeasures, in this case, what I suppose is to insert a ring beam or equivalent to any possible horizontal bracing at this level, or a ring beam. So any element which is able to create a rigid floor at this level in order to constrain the out of plane behavior, so that the behavior changes from 1 inch at the base of the wall through the case of 1 inch at the base and 1 inch at the center part, or in a certain, let's say, location that has to be identified from calculation, so more or less in the center of the wall. So this really increases the resistance of the wall, as you know, and this is proved by the results of the analysis. Even the linear static analysis provide risk index greater than 0.5, and if we go to the linear kinematic analysis, again the values are very high, and if you go to the nonlinear analysis, the building is almost compliant with the design epoch. So it's very easy to insert bracing or ring beams on top of this wall in order to restrain the out of plane behavior. But the results in terms of global behavior of this stiffening is such that the period of vibration of the building decreases, so the building goes in the higher part of the spectrum, so there is a higher response of the building, and the risk index a little bit decrease. with respect to the case without this stiffening on top, and this is understandable. So at the end, this risk index reached the value of 0.44. So summary of results. Summary of results are associated also to the cost of intervention. So each intervention has some risk index in terms of calculations for the in-plane, for the out-of-plane, and then has some cost associated. So what is basically the result? That with some limited cost, the increase of capacity, the increase in risk index is really significant. If we let's say consider the belfry. If we intervene on the belfry, we already reach 30% of the safety level of a new building. Then all the other interventions increase slowly the resistance of the building. Increasing the shaft of the tower will not provide any significant increase, but allow to move the critical elements from the tower to the wall of the palace. So it is necessary if you want to increase further the resistance, and then the intervention on the palace start becoming very costly because they have to be widespread. The injections has to be everywhere, and the fiber reinforced material again probably has to be quite widespread. So the cost increase very much, and the increase in capacity cannot reach this let's say this values of almost 0.4. And the total costs are more than 2.5 million euros, including all the technical expenses and all the additional survey that may be implemented and other things. I think they reach far more than 3 million euros. And so, what are the conclusion? Obviously, the seismic behavior of these palace and towers, but also the damage suffered by recent earthquakes, show that there are some vulnerabilities. Even visual assessment of this building show that there are some seismic vulnerabilities. But in any case, all the interventions has to somehow comply with the historical value of the building. So not all interventions are possible, and one has to find interventions which are not intrusive, which are compatible with the original matter of the building. There should be no loss of material. So we are a little bit limited on this. And to understand exactly what can be done on the building, some incremental intervention analysis has been considered. At the end, at the cost of more than 3 million euros, the maximum risk index that can be achieved is in the order of 0.45. This value could be acceptable from the technical code point of view, because as I told you, there is no limit in this value according to the code, but the municipality considered this value a little bit too low for the strategic use of the building. What does it mean? That if the use is strategic, this use should be continuous during the emergency, and it means that it should be operational during the emergency. But if the risk index is 0.45, it's almost sure that during the design earthquake there will be damages such that the building will not be operational anymore. So obviously it could be operational for smaller earthquake, but not for the design earthquake. So in case of ordinary building, one could have been accepted the use of the building with a limited capacity, but in this case, as I told you, for the strategic use, municipality has considered that this risk index is too low. What do I want to mean also for this? That I totally understand that, and I'm fully in favor of the fact that in historical buildings you don't have to reach a specified safety level because of the protection of the buildings, of the historical cultural value of the buildings. But there is no rule, no indication, no obligation to use the building as a strategic building in case of emergency. You may use additional building. So this is really your choice. It's the choice of the administration, the choice of the municipality. And in this case, Cingoli municipality made a very, in my opinion, let's say appropriate choice, saying that for strategic use it's not acceptable. So what they decided the municipality, basically to displace and to change the location of the offices that are important in case of emergency. Not all the town hall offices are important in case of emergency, but for example the technical office, all the offices that has the list of the citizens, the offices that deals with let's say citizens with maybe some problems, all the information that may be needed to manage the emergency, maybe the local police, all these offices are important during the emergency. So these offices will be relocated according to decision of municipality in a new building. So at that point, the use of that building will not be anymore, even if use as a town hall will not be anymore strategic during an emergency. And this means that the important class of the palace will lower from 4 to 3. Importance class 4 for the town hall use, for the strategic use, will not be anymore applicable, and so it remains only the use of the museum. Which again could be questionable, but it's not a municipality museum. It depends on ministry, on the Ministry of Cultural Assets. But just considering this reduction from importance class 4 to 3, there is a reduction of return period from 950 to 712 years, and the reduction in seismic action is in the order of 15%. So the capacity remains the same, but the demand will change. And the demand is now 15% less. So the risk index, it increased 15% more. So just because of the use of the building, they changed the use of the building, there is already some increase in risk index. And the intervention on the buildings will be done for sure, but because of this increase in risk index due to the relocation of the strategic use, probably intervention could be limited to the tower, to some connection of the tower to the palace, and some injections of maybe not all the walls, maybe of few walls. So in this case, if we compare the two alternatives, one alternative is to keep all the strategic function in the palace and to strengthen the palace as much as possible, or to have limited intervention in the palace and tower, and at the same time build new buildings for the strategic use or the strategic function of the municipality. Then if we compare these two options, the total cost will be almost the same. The overall safety level of the palace plus tower will be more or less similar, because there will be less intervention on the palace, but at the same time, not being strategic use, the important class will lower, so the demand will lower, and even all the critical function of the municipality will be now in a fully safe, in a fully safe buildings, in a buildings compliant 100% with the standards of the new codes. So this is really an additional value, because in any case, the safety level of this critical function of the palace, and so also the critical function, cannot be more than this 45%. So in any case, as I said, probably the palace will be not operational during emergency, and in this case, relocating this function in a new buildings, at least nominally, they could be operational during the stronger work. So at the end, this is the conclusion of this study. It has been a way to compare alternative solutions in terms of not only interventions, but also use of the building, allocating or relocating strategic functions, and at the end it is also always a compromise between the use of the building, the cost of intervention, and the safety level, and someone has to consider in detail this issue to take decision. So it's not just the engineer that say, okay, this is the best intervention, and then we continue using that building in that way, or in the way it was before, because there are always possibility of relocating, changing, doing different interventions. So it's important that the administration and the engineers work together in order to have a clear picture at the beginning of the different alternatives, and then takes decision based on science, based on results of the analysis. With this, I conclude all this case study presentation. I thank you, the municipality of Cingoli, for having provided or make available all this information, and I thank you also, all of you, for your attention. See you next time.